So good day, everyone. In the previous video, I have shown you this linear regression model, which is in the notation which uses the notation for gradient descent. So we can estimate a certain response y with this equation theta 0 and theta 1x. So this equation equals h of x is essentially a linear relationship between the predictors x and the response y. So we can say that we have found the best na regression line if we have also found the optimal na parameters theta 0 and theta 1. And by optimal, that means that the line is close to the data points and that the errors are minimized. So the errors are essentially just the difference between the actual and the predicted. So one way for us to measure the error is to use a mean square na error, and which is a cost na function. Okay, so the MSE for gradient descent is can be denoted with j of theta, wherein it is equivalent to the sum of the squared na differences between the actual and the predicted, and taking the average of it after. Okay, so note that this y hat is equivalent to h of x is equal to theta 0 and theta 1x. So what we want to do is to be able to minimize this cost function j theta by finding the proper values of theta 0 or theta 1 or the theta in short. So now, we can simplify the regression model by removing the intercept or bias theta 0. So then if we have this model wherein we have the hypothesis y hat is equal to theta 0 and theta 1x, wherein the parameters are theta 0 and theta 1. These are the weights that we want to estimate. And the cost function is, of course, is already shown here. And our goal is to minimize this theta j of theta 0 and theta 1 with respect to the change in theta 0 and theta 1. Okay, so removing the intercept or bias or theta 0, as you can see, this is how it looks like without the bias. Okay, so we then have this simplified na version. Instead of theta 0 and theta 1x, we have only theta 1x, canceling out the theta 0. And the parameter is only 1 with theta 1. And the cost function, we have j of theta 1. And our goal now is to minimize the cost function with respect to theta 1. Okay, so theta 1 ito dapat. Now, in the following slides, we will see that as the regression line gets closer to the data point, the cost function also gets closer to the minimum. So the cost function of such linear regression model, j of theta 1. So the gradient na descent tries to modify the values of the parameters theta iteratively towards the smallest value of the cost function j of theta. So we can see here that at first we have here a function of x, h of x with a function of x. We can see that the values are far away from the, this line, this is the regression line, it is far away from the values. So we can also see here on the other side is the cost with respect to the change in the theta. Okay, so as you can see, at first we have this regression line which is lies on the x-axis, and we still have the cost here given that the theta 1 is at 0. Okay, and as the line gets closer to the points, as you can see, the cost also decreased. Okay, and that is in response to the change in theta. So now that the theta is here, the cost function has also, the cost has also decreased. Now, we can see that the line now lies or very close to the data points, and the cost has also reached the global minimum. Okay, and this is again in response to the change in the theta. So in the following slides, on the other hand, we will see that as the regression line h of x gets closer to the data points, the cost function j of theta 0 and theta 1 also gets closer to the minimum. So in this case, we don't assume that the theta 0 is equal to 0, or we don't remove the bias. Okay, so we had the original form. So the hypothesis will then be y hat is equal to h of x equals theta 0 and theta 1x. So the parameters that we want to estimate is theta 0 and theta 1. And we want to minimize the cost function, right, given theta 0 and theta 1 using this formula, MSE. And our goal is to minimize the cost function j given theta 0 and with the optimal theta 0 and theta 1. Okay, so now we can see here some data points, and we have the estimated regression line, which is in the blue line. Okay, and then on the other hand, this part is the cost of function given theta 1 and theta 0. So our goal is to be able to reach this global minimum. So at this point, you can see that the fitted regression line is very far away from the data points. And we can see that the cost function is also very large. So given the theta 1 and this theta 0. So as we change, as the regression line gets closer to the data points, we can see that the cost is also changing or slowly converging to the global minimum. Okay, so that's what we want. So as that's what we want, that the regression line is very close to the data points, and of course that means that the cost is also decreasing, okay, or getting minimized, and that this cost is changing in response to the changes in theta 1 and the theta 0 also. Okay, so now this is the gradient descent for linear regression. So we have some function j of theta 0 and theta 1, and we want to minimize this cost na function j. Now, we start with the initial random values for parameters theta 0 and theta 1. So we can start with values of 0 for all of our weights, or we can assign random na weights for theta 0 and theta 1. Okay, and now we update or change the values of these parameters in a way that yield to a smaller value of the cost function j. And we will keep on changing or updating theta 0 and theta 1 and to reduce or minimize the cost function until we hopefully end at the minimum. So assuming here we have for only one predictor, assuming we only have one predictor, okay? Of course, each of the bias and the predictor will have associated na weight or theta, okay? And we take the weighted na sum of the predictor and the theta, so we'll have this regression line or regression equation for one predictor, and with a bias equals theta 0 plus theta 1x. And we can perform predictions using this linear regression line. So we simply have to plug in the values of x in here. And now, of course, we have to calculate the weight first. Calculate the cost. And that's by using the MSE for the gradient descent. Okay, so we simply have to plug in the actual value y and the predicted y, and then the x values. Okay, now given that we want to minimize that cost, we have to compute the change in weight. Okay, and the change in weight is simply the current weight minus the alpha or the learning rate times the partial derivative of j of the cost function with respect to the change in theta. Okay, and after changing or computing the change in weight, then we have to simultaneously update the weights for theta 0 and theta 1. And we are going to do this iteratively until we arrive to a global na minimum or reach some iteration. Okay, so this part, this notation is a symbolic na form for denoting a partial na derivative. So this is essentially the partial derivative of the cost function j with respect to the change in theta 0. On the other hand, this one is the partial derivative of j given theta 0 and theta 1 given the change in theta 1. Okay? Now, this partial na derivative actually is equivalent to this. So the partial derivative of the cost function with respect to the theta is equivalent to 1 over m times the sum of the differences between the actual and the predicted. And for the predicted, for the theta 1, this is for the bias, theta 0. And for the predictor x, the weight for the predictor x, this will be the partial derivative. So we have 1 over m times the error or the difference between actual predictor times the feature values x, okay, and you take the sum. So this whole equation is simply the equivalent to the dot product of the error y hat minus I times x. So we can rewrite it like this one. So we have, let's say, okay, and remove. So this is equivalent to this part, I mean. This will be equivalent to error transpose. So insert equation. We have y, oops, I minus y okay. So this will be basically equivalent to the dot product. So this will essentially be equivalent to the dot product of the error y hat minus y and x. Okay? And of course, you have to multiply this to 1 over m times the alpha. Now, what is the impact of changing the values of the parameters theta in order to minimize the cost function j? And how can we change the value of the parameters theta in the first place? So as I have already mentioned, we do this by computing the partial derivative. Okay, so this is denoted by this symbolic notation. We have the partial derivative of the cost function j with parameters theta 0 and theta 1 with respect to the change in theta sub j. So this numerator, the upper part, is derivative or change in the cost function, while the partial derivative of theta sub j is the derivative or change in the value of the parameter theta j. So this will tell us how we need to modify the parameter theta j to achieve a smaller value of j theta. So we nudge the weight a little bit and see the effect on the cost function. Okay, so let us unpack this one by one. And by understanding each variable of this partial derivative, okay, so moving on, we are going to focus on this part first, okay, computing this partial derivative and try to understand what this actually means. So at this point, this is the current value of the theta 1. So the point at where the theta 1 is right now. So given this theta 1, this is also the cost function with respect to the theta 1. Okay, so now this change in theta sub j, that means that we are going to change the theta. So we are going to change it. And then the change in the cost function. So the change in the cost function j with respect to the change in theta. So that will be the j of the partial derivative of j given these parameters, given the change in the theta that we did earlier. So we changed the theta. So that means that there will also be a change in the cost function j given theta 1. So in other words, how much error will be reduced given a little nudge in the parameter theta 1. Okay, so in essence, the value of the first derivative with respect to theta j tells us if theta j needs to decrease or increase in order to achieve a smaller value of theta 1. So the value of the first derivative tells us the direction of the change of the variable theta sub j, increase or decrease. So either tataas siya or bababa siya, or if dito naman, ganitong direction ba or ditong direction. Okay, so now, after we have computed the partial derivative, so we minimize the old theta sub j with the computed derivative by simply taking the difference, of the value and the partial derivative multiplied to the learning rate. Okay. Now, what is the impact of this learning rate? So why do we need it? So the learning rate will tell us how much of how much the change should be. So, or how big a step should we take. So if, for instance, if this is the j of theta 1, and assuming that the learning rate is large, so the tendency is the theta 1 changes a lot and probably faster. It will move faster on each step. So hence the gradient descent will potentially overshoot the minimum and accordingly fail to converge. So we will not be able to reach this global minimum. Okay. So on the other hand, if the learning rate is too small, then the theta 1 changes only tiny bit on each step. So hence the gradient descent will render slowly and will also take more time to converge. So we can set an alpha between 0 and 1, say 0.5 or a little more or less, hence not very small or very large. So now we already understood what the partial derivative is, right? Assuming that you actually understood it. Now, what does this equate to? Okay, so what is the partial derivative of the cost function with respect to theta j? So we know that the cost function is equivalent to this equation. We have 1 over 2m times the sum of the squared and differences between the actual and the predicted. So we are going to plug that into our equation. Okay, and now we have this equation now. And we know that the h of x is equivalent to theta 0 and theta 1x. So let's plug that into here also. So we now have this updated equation. And we know that this theta 0 and theta 1x is simply equivalent to the predicted y hat. Okay, so plugging that in. So now this is the partial na derivative. Okay, so now what would be the derivative given that j is equal to 0 and j is equal to 1? So given j is equal to 0, then the theta sub j will be equal to, wait lang. What is this? Okay, so given that j is equal to 0, so that means that theta j is equal to 0. So we update the theta 0. So what will be its partial na derivative with respect to theta 0? So now, given theta 0 and theta j equals 0, theta j equals theta 0, then the partial derivative of the cost function is simply 1 over m times the sum of the errors. Okay, and what if the j is equal to 1? So that means that theta j is equal to theta 1. So this refers to the weight of the slope, right? I mean the weight or the slope of the corresponding feature x. So the partial derivative of the cost function with respect to theta 1 is equal to y hat minus yi, or the difference between actual and predicted, times the x, and take the sum. So this is essentially equivalent to the dot product, right? Dot product of the errors and the x. So going back to here, we have here, right? Oops, dito yan. Ayan. So equivalent siya dito. Ayan. So it is equivalent to this part. So kung i-rewrite natin to siya, it will then be there it is. So this will be equivalent to this equation. Okay, and this is just the error, right? Okay, now the whole computation for the partial derivative is as follows. So we have theta j minus the alpha, or the learning rate, times the partial derivative. Okay, and we know that the cost function is equivalent to this equation. So plugging that here, replacing this j of theta with its actual value. And now replacing h of x with theta 0 and theta 1x. And we arrive to this, and we replace this again with y just to simplify the equation and we can understand it better. Okay, so now we want to get the partial na derivative given a value j is equal to 0 or j equal to 1. So if j is equal to 0, so we simply replace j with 0. Okay, and it is equivalent to this. The partial na derivative is essentially equivalent to 1 over m times the sum of the differences or the errors. Okay, and if j is equal to 1, on the other hand, we are going to get the partial derivative of this cost function j with respect to theta 1. Okay, and then this is equivalent to this partial derivative is equivalent to 1 over m times the dot product of the error and x. Okay, so we're in this part is the part where we update the bias, and this is the part where we update the weight or slope of the feature. So if you want to see a full derivation here, so like how the derivatives were computed, then You can visit the site or some other materials in the internet or YouTube and some books. Okay. So now the basic procedure of gradient descent for your review. So we initialize the random weights, theta 0 and theta 1. We update weights until convergence is reached. We have the bias and predictors, and each having weights. Taking the weighted sum, perform the predictions using the weighted na sum, and then calculate the cost. There should be a cost here, and compute the change in weight by computing the partial derivative of the cost function with respect to the change in the theta. Update the weights, do this again and again until we reach some convergence or reach some number of iterations. And this partial derivative evaluates to this part. Okay, wherein if it is theta 0, then we have this change in weight. We have y. Yeah, you already know this one. The sum of the errors, okay, divided by m. So essentially the average. And then for the theta 1 is the dot product of the error and x, okay, times 1 over m times the alpha. So now for the gradient descent for multiple linear regression. So previously we only had one predictor x. So what if we have several predictors? So each of these predictors will have their associated weights theta. Okay. So for convenience of notation, we assign x sub 0 is equal to 1. Okay, so for the bias. So we have a set of x, a vector na x and a vector theta. And we take the weighted na sum, and it is essentially equivalent to theta transpose and x. Okay, so if we only have one predictor, we have this formula for repeating, updating the weights. We have theta 0 and theta 1. For if we have multiple na predictors, then we only have one. Simplify it to one equation. We have theta j equal to theta j, or old value of theta j minus the dot product of error and x sub j. Okay, so now we simultaneously update for all the weights j equal to 0 to n. So this is it for this is the algorithm for the multiple linear regression. So we have several na predictors, x sub 1 to x sub j, each having associated weights, taking the weighted sum, perform predictions, calculate the cost, and this is how we can update the weights or compute the weights. This is already the computed na partial derivatives. Okay, so for all theta 0 to theta j, we use this equation. Okay, and then update the weights simultaneously, and iteratively do this until we reach some iteration. So things to remember, we have the h of x. This is our linear model representation, which may be represented in matrix form, theta transpose x. And our cost function is MSE for the gradient descent. And the gradient descent for linear regression, with multiple predictors is this. So we have a theta j minus alpha times 1 over m, or this is actually the average, right, of if we divide to 1 over m. Okay. Now, given the m training examples and features, so in gradient descent, we need to choose alpha or the learning rate, and we need plenty of iterations, and it works well when we have a lot of predictors or a lot of features. And okay, on the other hand, if we use the ordinary least squares or OLS, that uses a closed form solution, so there's no need to choose an alpha or learning rate, and there's no need for an iteration. Okay, so the only problem is that we need to compute for the matrix na inversion which is a very expensive operation. And it is slow if n is very large, okay, or if you have a lot of predictors. So that's all. And if you cannot still understand this, then just email me and ask me which part you do not understand or you are still confused with. Okay.